Okay, so that was 6. I'm going to keep going. 8. It's already trying to slow down. There's 2 more. That's 12. 14. 16. Here's my guess of 18. Still reacting, so my guess was too low. My hypothesis was too low, although it's slowing down quite a bit with each. And 20, it's still reacting. Let's do 22. And still a little bit of sound, but I think it's basically just the water shaking around. So I'm going to say 22 milliliters to 1 gram of baking soda, which is the same as 22 grams of vinegar to 1 gram of baking soda. This is my magic ratio. Okay, I'm going to do part 2, and that has 2 grams of baking soda. So my prediction here will be double 22 grams of vinegar, which is 44 grams of vinegar. So let me do 2 grams of baking soda. So here is 2 grams of baking soda. I'm going to dump it in my reaction vessel. And here I'm going to go 3 milliliters at a time. 6, 9, 24, 39. Should be getting to where it will slow down. That's 42. And let's go to 45. And yeah. So pretty much quiet at 45. So yes, indeed, about double the volume of vinegar if I double the volume of baking soda. So it looks like there is a perfect ratio, and that ratio is 22 to 1, 22-ish to 1, which is the same as 44 to 2. So we have found that perfect ratio. So after concluding and analyzing the many experiments in this course, this whole course, the chemistry of atoms, we've pushed far beyond medieval alchemy. That's where we started, and have built up a radical idea to better match our findings. And this idea is the atom. Again, not revolutionary in the 21st century, which we are in, but in the realm of human history, just amazing to be able to have this much proof that atoms exist. So let's take a step back and see how far we've come. So we began our journey in chapter 1 with Lavoisier's mass experiments on this system, baking soda, vinegar, and steel wool and oxygen. So with those two systems, we showed that mass is conserved in all chemical reactions. And this is a critical mathematical foundation, really, for all of chemistry. So we pushed this idea further in chapter 2 to claim that the number of atoms is conserved in chemical reactions as well. And using this foundation, we're able to create chemical equations to keep track of and predict chemical reactions involving specific types of atoms. So this idea of the conservation of mass and the belief in atoms allows us to actually picture what's actually happening in terms of how the atoms are moving around in any chemical reaction. No small accomplishment for human chemists. So we then took up Humphrey Davy's electrochemistry in chapter 3 and broke apart water molecules using the power of electricity and our newfound knowledge of the atom. In chapter 4, and even just saying break apart, that also is just kind of suggestive that atoms exist. What are you breaking apart? You're breaking out molecules into atoms. In chapter 4, we explored how atomic theory helps explain the way chemicals react in solution when the concentration or temperature is changed using kinetic theory. So we just use this idea of space. So spatial distance between things might indicate that atoms exist. So if things are farther apart, it'll take them longer to get together. And as soon as you say it was it, it's longer to take the atoms together. And then finally we rejoined Proust and the atomists of the early 1800s to defend our atomic theory by demonstrating that chemicals do in fact react in a fixed predictable ratio, just as atomic theories suggest. So if nothing else, in this short course, The Chemistry of Atoms, we have proved, I wouldn't say prove, that's a strong word, I'd say we built a very, very, very strong case for the existence of atoms. So if any atomic denier comes at you, you can point to 5 chapters, 10 experiments of data which suggest strongly that atoms do exist.